Welcome back, class. So we were studying about the frequency domain representation of the signals. Okay, in the last chapter we learned about the Fourier series. So Fourier series was basically if we have the periodic signal, so we can get its frequency domain response. Okay, or we can decompose this periodic signal into its basic primitive components. Okay, so we have learned about the three kinds of the Fourier series. Okay, the first one was the complex Fourier series. The second one was the combined trigonometric. And the last one was the trigonometric. So we have learned that we can decompose any periodic signal into the Fourier series form, and then we can actually plot the spectrums and the other components, and we can analyze any LTI system. Okay, we'd have like if the input response of the LTI system is like in the form of the periodic or any other kind of the waveforms, like the square wave, triangular wave, and you want to get the output. Okay, and let's say the impulse response of the LTI system was h of t. Okay, so then we can get the output, okay, with the convolution of the input signal with the impulse response, right? And so basically we get the transfer function of the impulse response h of omega, and then we multiply with the x of t so that we can get the output. Okay, so basically all it was about the frequency domain representation of the signals. So Fourier series is only for the periodic signal. Okay, what if we have a periodic signal? Okay, what if we have a periodic signal? For example, this exponential signal. Okay, for example, let's say this triangular signal. Oh, sorry, this rectangular signal. Okay, let's say a triangular signal. Okay, or like I have just an impulse. What if my input is just like the aperiodic signal? Then what will happen? So for the aperiodic signal, we calculate the Fourier transform. Okay, we calculate the Fourier transform ft. For the frequency domain representation of the signal, of the aperiodic signal, we calculate the Fourier transform. So this is this chapter, chapter 4. So in this chapter, we are going to learn that how for the aperiodic signal, we can get the frequency domain representation. Okay, why we are getting frequency domain representation? So like we have learned earlier on, so basically in frequency domain, the analysis is very easy. Okay, let's say this is my input signal of the LTI system, and this is my output system, and this is my impulse response. Okay, so last time we have learned that, so basically in the time domain, the output is what? Input convolved with the impulse response, convolution. Okay, but if you just calculate the frequency domain of this, okay, frequency domain representation of this signal, let's represent using x of omega. Frequency domain representation of this, let's represent using h of omega, and the frequency domain representation of this, so let's represent y of omega. So we can get the output signal by just multiplying the input signal. Okay, just simple multiplication of the input signal with the frequency domain representation of the impulse response of the system h of omega. So convolution, we guys have learned that convolution either in the integral form or in the graphical representation is a complex procedure. Okay, but if you go to the frequency domain, so just multiply. So just multiply, you will get the frequency domain output response. Okay, or like if the input is changing, so just keep on multiplying with that, and you will get the output response. So here we are going to deal with these things. Okay, so basically, although Fourier transform is mainly for the aperiodic signal, but we can also calculate the Fourier transform of the periodic signal also. Okay, so let's see what we are going to see here. We are doing this, as I explained here, for the simplification of the analysis of the signal and system. Okay, if you go to the frequency domain, our analysis will be easier. Okay, that is the main purpose. Okay, simplification of the mathematical analysis. Okay, that is the main purpose, and it has wide range of applications. Okay, this Fourier transform, the frequency domain representation of the signal. It has wide range of application in electrical engineering, particular in communication signal and systems. Okay, so the main advantage is if you know the frequency domain representation or h of omega, which is actually called as transfer function, as explained in the last lecture also. So basically transfer function I can also write as the output our input. Okay, output our input, that will be my transfer function. So if I know the transfer function, I can get the response, output response for any input. Okay, so that will actually be a very easy and quick procedure. So if you want to calculate the Fourier transform of signal f of t, okay, aperiodic signal, okay, so just multiply f of t with e to power minus j omega t, okay, and we will get the f of omega, its frequency domain representation, f of omega. Okay, so f of t is time domain representation, and if I take its Fourier transform, I will get f of omega, frequency domain representation. This is called frequency domain representation. This is time domain representation. Okay, if I have time domain signal, if I take its Fourier transform, this is the symbolic of the Fourier transform, we will get the Fourier f of omega or the Fourier transform of the time domain signal. Okay, frequency domain representation. So how I can get f of t multiplied with e to power minus j omega t. This is called analysis equation also. Okay, and if you have frequency domain response and you want to get the time domain, if you want, so I get frequency domain response here, but if we have a frequency domain response, you want to get the time domain response, so what we can do, we will multiply frequency domain response with e to power plus j omega t. Here we are multiplying with e to power minus j omega t. Integrate and divided by 1 over 2 pi here. We will get the f of t, time domain signal. So this is called inverse Fourier transform. This is Fourier transform. This is called inverse Fourier transform. See here, if I take the Fourier transform of the time domain signal, I will get f of omega. Okay, the frequency domain. If I take the, this is the Fourier transform. If I take the inverse Fourier transform, I will get the f of t. Okay, so this representation, this notation is actually also called as the FT pair, Fourier transform pair. Okay, what is the Fourier transform pair? Fourier transform pair is that if I have input f of t and if I take its Fourier okay, this double arrow is presenting the change of the domain, and here we can put the f like in this form. So if I take the Fourier transform, I will get the f of omega, and if I go back, reverse, inverse Fourier transform, I will get the f of t. So this is called Fourier transform pair notation. Okay, so we are going to use this thing again and again. So important thing is, whatever time domain signal have, multiply with e to power minus j omega t, and you will get the Fourier transform of that signal. Okay, so basically for the there are some conditions. Okay, and if your signal f of t, whatever signal you are having, if that condition if it's satisfying 3 conditions, then only in that case we can calculate Fourier transform. The first condition is your signal should be bounded. Okay, and it should have a finite number of maxima and minima. Okay, if it is like if you take the derivative, so it should have the finite number of maxima minimum, and it should have finite number of discontinuities, and it should be absolutely integrable. Okay, so basically this is the condition of the bounding. Okay, if you guys remember from the chapter 2 and chapter 3, that if your condition is bounded, okay, or stable, okay, absolutely integrable also identify the stability of the signal. Okay, so if your signal is satisfying these conditions, then only in that case its Fourier transform can be existing. Okay, so let's see the first example. Okay, the calculation of the Fourier transform. Let me solve this example in live session for the rectangular signal. Let me solve this example. Okay, with the impulse. Okay, so what is this? It's just an impulse. Okay, at t is equal to 0 with the weight of a. I want to calculate this Fourier transform. So what is the formula? I will integrate from minus infinity to infinity f of t e to the power minus j omega t into dt. Okay, so what is f of t? F of t is this impulse function. So I will replace my f of t with impulse function times e to the power minus j omega t times dt. Okay, so remember the impulse properties. Whenever an impulse multiply with the function, so what is happening? Okay, let me use the shifted impulse here. So we will get the function value at the impulse location, right, with that impulse. Okay, this is the one property of the impulse. Second property is, okay, the same. If you are integrating an impulse from minus infinity to infinity, that will be equal to 1. Okay, so here a is a constant, so I can take a's out. So rest is minus infinity to infinity impulse a to the power minus j omega t into dt. Okay, so here this is impulse and this is multiplying with this function. So what will we get? Function value, this function value at the impulse location. So what is the impulse location here? T is equal to 0. So what will we get here? Minus infinity to infinity, this impulse with the function value at the impulse location. So t is equal to 0. Okay, because this impulse is existing only at t is equal to 0 with the integration. So a to the power 0, it will be, this will become 1. So what I have got here, a minus infinity to infinity integral of the impulse. What is the integral of the impulse? 1. So basically a multiplied by 1 is equal to a. Okay, so the Fourier transform of an impulse function is what? A constant. Okay, so this is the time domain representation. Now if I draw the frequency domain representation, so this is the omega frequency. So here what is the frequency domain response? Magnitude is a constant with the value of a, whatever the weight of the impulse is. For example, if the impulse is 2 of sigma of t, so this will be equal to 2. So in time domain, impulse is existing at t is equal to 0. In frequency domain, okay, frequency domain representation of the impulse, the Fourier transform of the impulse is what? Capital A, or a constant time. Okay, so if I want to write this in the form of pair, so I can write that impulse is the time domain. If I take its Fourier transform, I will get a constant. Okay, I will get a constant. So this is the first Fourier transform pair which we have learned. Okay, this is another example if we have a shifted impulse. Okay, so try to solve this. We will try this example also in the live session. We have solved the example for the simple impulse. What if we have a shifted impulse? So try to get what will be its Fourier transform. Okay, we will also solve this rectangular example in the live session. Okay, then this is the exponential. Okay, so try to solve this example. Okay, exponential, and we will solve all these examples with another example of the inverse Fourier transform, okay, in the live session. Okay, so that is actually first part of this lecture, that how we can actually calculate the Fourier transform of any signal. Okay, the examples will be solved in the live session. Thank you very much for your time.